Soil bulk density is defined as the mass of soil per unit volume in its natural field state, including air space and mineral matter, plus organic substance. High values of bulk density may restrict the movement of surface waters through the soil, leading to a loss of nutrients by leaching. It may also increase erosion rates. Bulk density measurements are very important for assessing soil quality, since root growth and penetration of soil, together with the ease of soil aeration, are largely controlled by this factor. Geotechnical properties provide another important control for erosion. Atterberg limits, for consistency, swelling, and slaking behavior are considered in many badland studies. Certain minerals play an essential role in the breakdown of some rocks at near-surface conditions. Some minerals are important because they may become soluble, like all soluble salts, halite, but also moderately soluble like sulphates, gypsum, or carbonates, calcite and dolomite, especially when they can be dissolved because of the small size of their constitutive particles and or solvent characteristics. Some other minerals, like clay minerals, smectite in particular, can absorb water in amounts several times their dry weight, with consequent volume increases. Wetting-drying alternations in materials with expandable clays cause the formation of nets of deep cracks and may also lead to the formation of a shallow layer of loose expanded regolith fragments, usually called popcorn. It was found that the percentage presence of the swelling clays in the overall material mass is very important. Where clay percentages are high, the material mass is rendered impermeable on swelling, encouraging surface wash erosion and reducing infiltration. Where clay percentages are low, the deflocculation of the clay fraction merely destructures a material already lacking in other sources of cohesion, encouraging subsurface erosion. Given the presence of a suitable hydraulic gradient through a site, this distinction will separate materials that are dispersive but which do not develop large pipes from those that do. Clay dispersion is a physico-chemical process relevant to erosion processes, particularly to the development of pipes. Materials, soils, regoliths or rocks, with a potential to disperse are those which contain a high exchangeable sodium percentage, ESB, saturating part of the exchangeable cations of their clays. This percentage is considered to be critical when higher than 13. To predict the tendency of materials to pipe, Faulkner et al. Explored the effectiveness of the relationship between electrical conductivity, EC, and SAR, sodium adsorption ratio, originally used by Rangasamy et al. Whilst this improves diagnosis over the use of ESB or SAR values alone, it seems that this analysis is also insufficient in itself to distinguish between badland surfaces in terms of their morphology. The relationship between pH and SAR can be used to indicate the extent of material buffering as dispersivity changes. In the analysis of the processes connected to the land degradation, many models were developed in the past with the objective to give a qualitative and quantitative solution to the problem of the soil loss and erosion. This estimation of those phenomena is particularly difficult due to the number of variables to consider and their typologies including both natural, i.e. soil nature, vegetation and rainfall, and anthropic ones, as the many options for management practices and land use. Models about this evaluation are often based on empirical or process-based analysis, and the synthetic equations used to describe the phenomenon are necessarily complex because they have to include the interactions of all the parameters. Besides, the complexity of the erosion processes, and the need for huge data banks to compile the many algorithms which are included in the models, are also technical problems to consider in the analysis plan. Anyway, many erosion prediction models are available, event-based or long-term models, empirical or physically based models, on a basin or plot scale, which have been improved in the last few decades. One of the best examples in the estimation of long-term average annual soil loss from arable lands, is the Universal Soil Loss Equation, USLE, model. The Universal Soil Loss Equation, USLE, developed by Wischmeier, Smith, and others in the 1960s, predicts the long-term average annual rate of erosion on a field slope based on rainfall pattern, soil type, topography, crop system and management practices. In the applications related to the analysis of erosion processes, the USLE equation was replaced by the revised Universal Soil Loss Equation, RUL, which has a similar structure, that is a black box factor empirical model, but with more sophisticated inputs, and it is designed for operation on personal computers. Because there is a wide discrepancy between predicted and observed erosion rates, Models are better as research tools than as public policy and regulatory instruments or for prescriptive design measures for constructed landforms. But some models may provide useful guidance for the design engineer if adequately calibrated and verified for local conditions and if the design accounts for the uncertainty.